So as already I have introduced Ashutosh to you, he actually joined us in 2019 as a winter intern, and he actually spent around a semester with us, and he was the one who actually did a lot of work towards fixing the NGHDL feature of eSIM, and he was also offered a placement in the FOSSI group, but unfortunately he couldn't join. But still, he continues to work with us, and today he will be actually talking about how NGHDL feature is extended to incorporate microcontrollers. So, Ashutosh, please, the dais is yours.
Thank you, ma'am. Thank you. Basically, I was in my final year when I joined FOSSI as a winter intern in December 2019. And first of all, I want to say thank you to you, Usha ma'am, and Kannan sir, obviously. So because it was a very good work time I had working with you guys. So what I'll be sharing with you today is once why we had made NGHDL and basically showcasing its potential, what we can do with it. So my primary task for the internship was to implement a framework via NGHDL through which we could add microcontroller supports to eSIM. So as you can see, probably the motivation basically is as of now, microcontrollers are used everywhere in embedded electronics, and it is like every student, engineering student, regardless of any branch, or probably not even engineering student, do use microcontrollers as a project, be it as a part of curriculum or be as a hobby project. So the problem now is microcontroller is prevalent, but for simulating it along with all the analog circuit, there is a gap between the simulation software which is present and the demand. So there are commercial software available. As I'm aware, Proteus has this. Proteus is a very good commercial software um, which can simulate microcontroller. But the problem with this is since it is commercial, not everybody can buy it or get a license for it. So if for institutions, it's all right, but for individual hobbyists or small scale startups, it's very difficult. There's not a very good software present yet in the open source world for this. So that was the main motivation behind it. There are some softwares like GPU sim or MCU sim, but there are more focused towards just the microcontroller simulation, or basically microcontroller emulator, not a mixed mode signal simulation. So that was the motive. And before I explain about the framework, let me just talk about what we are expecting from a simulation point of view from a microcontroller. So as you all know, we have to program a microcontroller first. So before the actual simulation begins, we program with code and instructions. And during simulation, it takes input from the analog circuit. It performs all the processing based on the codes and the input signals, and then it provides output to the analog circuit, and the loop continues. All right. So keeping this in mind, I will tell you how we develop the framework. So from a simulation point of view, we can divide, basically we did this, we can divide it into two main parts: the input output pins of the microcontroller, which are the actual things that receive the input and output from the signals. And then we can model the internal or the core of the microcontrollers separately. And since we are going to simulate these two models separately, we need a link between them which can communicate. All right. So I will tell you why we chose this model, like why we chose to divide it. These are the reasons. So the main reason being NGSDL is already implemented in eSIM, so we don't have to develop another package from the ground up. And basically, what we are doing by splitting them is we are going to be writing what we wrote. The peripheral module or the output pins, input output pins, were defined in VHDL, and the internal processing was defined in C code. So what this does is it takes the best of both worlds. Like, as you know, like VHDL is a language made for digital input output and some slide processing also we can include. And the writing logic in C is very easy, and almost any student can do it. So we took the best of both of these languages, integrated it, and we also negated some of its bad points. Like in VHDL, it is difficult to write complex logic, and in C, it is difficult to interface the output with the actual simulator. Yeah, so these are the main reasons. It is with this framework, it is very easy to scale it up. If you want to implement this for new microcontrollers, you just have to write uh, the processing of the new microcontroller, and you can use the same VHDL layout. You can increase the input output ports. That's it. Okay. Yeah. Also, you get the advantage that in C code, since it is been the language has been used for so long, it is very optimized now. So the simulation time is very low. With this said, nothing is perfect right in this world. So this also has a few drawbacks. The major drawback being, since these are two different languages, we need to we had to brainstorm and develop a link between these two. Yeah, as you can see here, the peripheral module in VHDL, the core module in C, and there is a utility module in between them, which facilitates the communication. So just to give you a brief, this is how a typical simulation goes. So from the analog circuit, there is an analog to digital converter, ADC bridge that Saurabh had showed you guys earlier. From that, it goes to the NGSDL server to the VHDL. Then the VHDL module sends it to C. C processes it and sends it back to VHDL, and it flows back from digital to analog converter back to the circuit. All right. Saurabh, am I clear at this point? So yeah, this is a little bit more in depth on how it actually begins. So I won't go into too much depth. I'll just go from the surface. So what happens when you click the simulation? Sorry. Yeah, what happens when you click the simulation button is before the actual simulation starts, the software first initializes basically all the components that you have used in the simulation, all the code models, all of them are compiled. So during that time, uh, whatever, so we come, sorry, I forgot to mention this before, we program a microcontroller based using a hex code. So when we write a C code, it is then compiled into a machine level language that is a hex code. So that is put in the microcontroller. So before the simulation begins, the hex code uh, or the compiled C code is mapped into the microcontroller. Now, once the simulation starts, then the NGHDL or the VHDL block receives the clock signals. Yeah, once it receives the clock signals, it gives the core module, the C code, the command to run the computation with the current instruction that it has, or the current processing uh, regard according to the program counter, and on the basis of the inputs that it gets from the analog circuit. So it performs the computation, then the output is given to the VHDL code or the peripheral module. The output is given to the analog circuit. Then the loop goes back if again the clock cycle is present. So basically, it is a clock-driven process, as you can see. When the clock's pulses are given till the simulation till the end of the simulation time, and when it stops, this whole process stops and you get the output. So this is just a high level workflow. If I go into too much depth, it will be too much for now. But yeah, later on, if you want to contribute or if you have anything, you can contact the eSIM team. All right. So the framework was devised. Now we had to implement it, and we needed to test it with an actual microcontroller. So for that purpose, we took 8085 microcontroller. So why we chose this was because it follows the same architecture as that of Atmega 328P. Atmega 328P, as you know, is used in Arduino's. Arduino is probably the most famous microcontroller board for beginners. So it follows the same AVR architecture, RISC architecture, and the added bonus of it is, as you can see, it has 8 pins only. So the design complexity is reduced tremendously. I believe Atmega 328P has 28 pins. So developing something for that would take a lot more time. So this has the advantage that we could develop it in lesser time, because um, my internship period was just 6 months. So yeah, here is the diagram that we simulated. In the middle, you can see that is the microcontroller module. It is just written in VHDL. Probably if time permits, I can show you also. So this microcontroller block was written in VHDL, input ports, output ports, and it was interfaced on both sides. As you can see, ADC bridges and DAC bridges are there. From analog side, we are giving it supply voltage, ground, and pulse signals, or the clock. And on the output side, there is just a resistor just to check the output for a sample code. Yeah, here is the code. So what we are doing, simple, we're just setting the output high for 1 millisecond and then low for 3 milliseconds. And this is the sample output that we get. So it showcases that whatever framework we had made, and all the communication is happening properly, and also the timing is proper, as you can see. And this is another example. It's a bit advanced example, still relatively simple. It's just a buck converter. All right, the diagram that you see in the upper half of the screen is the buck converter, and below is the microcontroller part. Same thing, PCC, ground, and clock signals are provided to microcontroller along with the control signal this time. Like we were giving a control signal in the previous example, same control signal has been given. So based on the control signal, the microcontroller will vary the duty cycle of the buck converter, and the output will vary proportionally. So that you can see in this output. The red part is the signal given to microcontroller, and the blue part is the output of buck converter, which increases proportionally with the duty cycle. All right. Now, yeah, one important thing that I wanted to mention is that this is not the only way by which you can simulate a microcontroller. There are a lot of other ways. This is just one method that we all agreed upon. This is probably called as a logical implementation of a microcontroller, because we are not simulating all the internals of microcontroller, like there is ALU, there is a lot of other things. We are simulating the registers, those are important, but all the internals of microcontroller we are not simulating. So this will not be 100% accurate model, but from the output you can see it is accurate enough for day-to-day use, or for institutional use, or for hobbyists. Okay, so unfortunately I don't have the simulation files ready with me. So, but there is a demo that I had recorded it, so I can show you the demo. But before that, if you have anything, then I can answer. Shall I proceed? I just have a demo to show now, a demo of this entire thing. So yeah, so whatever I had said, I guess you can um, still it is in testing. Let me tell you, still it is in testing and development phase only. It has not been released in packaged in eSIM yet, but it is since it is open source, everything is available on GitHub. You can get in touch with either Saurabh or Usha ma'am, and they will let you know how to contribute. Let me just show the video quickly. All right. So it's a video from back when I was working on it and I recorded it. So this will also show you all the steps you would need to do when you would be actually simulating a microcontroller. Here is the schematic that I just showed you in my PPT. Same schematic. Yeah, this is the C code for it. It's a simple code, standard headers. You can specify the CPU frequency and everything. And the main function, we are just outputting the output pin high for 1 millisecond and putting it low for 1 millisecond. So now that we have our code, we need to compile it. We need to generate the machine instructions for it. So that I am doing it through the command terminal. All right, so yeah, this is the this is the compiled C code. On the right hand side, that is how the opcodes or the machine level codes look like. It's called the hex code. This is what is burnt or flashed into the microcontroller when you program it. And on the left hand side, it is just an explanation of the opcode. So basically, whatever you are seeing, like EC051 or EC01, that would be an instruction, and it is just explained on the left side what that instruction is, what it does. So while simulation, you don't need to necessarily do all this. It's just for your understanding how it is mapped and what it does. So this hex code, this compiled C code, we have to put it in our example folder before simulation. Yeah. So yeah. Then standard procedure from here onwards, you have to convert KiCad to ngSpice. You have to specify all the parameters according to your project. That I've already done. And then you can start the simulation. Now the simulation will take some time. It is a bit heavy. It's based on the step time and the stop time. So I'll just show you the output with, along with the code for better understanding. Yeah. So as you can see, how we had coded it, the high for 1 millisecond and low for 1 millisecond. The output also matches. So this is just for confirming whether everything like it's simulating properly or not. So there is a bit of time, so I can show you a couple of more things. So this is uploaded in GitHub as it is. Whatever you're seeing right now, it is uploaded in GitHub. You can use it. I'll explain what all is left and what all you can contribute. But let me just show you the codes. Yeah, so this is the VHDL code. Nothing complicated here. Just the input output ports have been defined, and it's just defined like it will operate on the basis of clock. That's it. And here is the C code. This looks big, but it's very simple. It's very easy to read. It's just basically instruction decoder. All right. So yeah, anybody who wants to contribute, yeah, you can contribute it. So what all has been done is as of now for the AVR microcontroller family, we have implemented all the instructions. Like there are some around 125 150 order instructions that we have completed, me along with few more interns, and we have implemented timers. I think the work on interrupts is going on. So interrupts and the analog input, basically it's a analog to digital conversion. So that part is left, interrupt part is left, and this is of as of now this has just been done for 801085. So what you can do is, if you really want, you can make it for the micro controller that Arduino uses at Mega 328P. You can use uh, PIC series of microcontrollers. Those are very prevalent. STM also. So there's a lot of potential here that you can do. And what you can do is, it's not just limited to just microcontrollers. You can implement basically anything you want. For example, if you want to implement a digital model which has a lot of complicated logic embedded in it, so that will be a difficult task to do if you were doing it just in VHDL. So using this framework, you can just write a C code for the logic, and you can just write a VHDL code for the input output ports. Yeah, so yeah, basically anything digital you can complicated, and in digital domain you can use this to implement it. I have told you whatever work is pending and it's still going on, so you can contribute. You can ask Usha ma'am or Saurav, they can tell you. All right, so that's it. If you have any questions at the end, we can answer. I'll stop sharing. Yes, ma'am, you can continue with the next part.